This is the lab report about the black hole done by Francesco Costantini and dubbed by Google Translate. The aim of this lab report is to determine the net force exerted on the star orbiting around the black hole and to determine its mass. In order to determine the net force acting on the star due to the black hole, Newton's second law of kinematics will be applied, but written as the following. Since delta P is equal to mass times delta V, I can write the force as delta P divided by delta T. As delta T grows smaller, I can write delta P over delta T as dP dt. And this will be translated in VPython. Delta P comes from the velocities calculated from the positions listed on the CSV file given. This is written as the following in VPython. The net force can be written as the sum of the parallel component of the force and the perpendicular component of the force. The parallel component of the net force can be expressed as the rate of change in magnitude of the momentum with respect to time multiplied by p hat. This can be approximated to delta magnitude of p divided by delta t all times p hat. P hat can be calculated as the ratio between p vector and the magnitude of p because of this representation. The parallel component of dP dt, since dP dt is equal to the net force. This can be written as the following on VPython. And this is how the perpendicular component of dP dt is written as. You might presume to translate this equation into this piece of code, however, we lack of the radius of the kissing circle tangent to the trajectory of the star. So we will write it as the difference between dP dt and dP dt parallel. Since dP dt and dP dt parallel are known in the code and since Fnet is the sum of its parallel and perpendicular components, this is how it is written on VPython. Fnet perpendicular is equal to dP dt perpendicular for the same reason applied on the parallel component of Fnet. But how do we determine the mass of the black hole? Br with Newton's law of gravitational motion is the answer. This is the relationship in terms of the magnitude of the gravitational force. Finding the mass of the black hole with VPython will be easy with all of the other values known. Since it is presumed that the gravitational force is the only one acting on the star, we will presume that net force is the gravitational force. This is how to determine the square of the magnitude of the distance between the star and the black hole. Then I isolate the mass of the black hole. All of this is translated as the following on VPython. Magnitude of Fnet, magnitude of r squared. The constant g, which is 6.67 times 10 to the negative 11, and the mass of the star, which is m in the code. Then the program is run. These are the values obtained for the net force, the yellow arrow in the program. For the parallel component of the net force, the black arrow, and the perpendicular arrow, the blue arrow. The mass of the black hole is circa 1.99 times 10 to the 31st kilograms. Although the net force and dP dt and their parallel and perpendicular components are respectively equal, Fnet, decomposed as Fnet parallel and Fnet perpendicular, is the agent acting on the star. dP dt is the effect deduced from the motion of the star. Here are some other differences, but now, if the black hole was replaced by another one, would the mass of the new black hole be different if the star data were the same? The answer is no, because since nothing has been changed except the black hole positions and velocities, the momentums are the same. Therefore, the new black hole would have the same mass as the old one. This is my lab report. Thanks for watching.